Hi, my name is Jorge Montoya. This time we are going to do a regional groundwater flow model with MODFLOW and MODELMUse. First of all, we are going to get a list of the tasks that we are going to do. First, this is a tutorial for regional groundwater flow model. The term regional is basically for the extension of the basin, because we are going to define that is I don't remember the exact area, but that defines the regionality, but this is a term that could be very different. This is this tutorial have these main tasks. The main tasks are to define a model extension by shapefile, because we are not in other models you define the grid from the beginning, but in this one we are going to use the no grid option, so we are going to define it by shapefile. Okay, the next step is we are going to import topography, our digital elevation dam. So this is a raster file. We are going to deal with that. And then we are going to assign like 4 layers. So this is 1 alluvial plus 3 fractured rock. And then what else? We have to define the layer types, define the aquifer types, the aquifer type, and vertical discretization. Okay, cool. What else we are going to do? We are going to, okay, we have defined this. We are going to set the hydraulic parameters. We are going to check the mod flow time, check the mod flow time, and check if we are going to in steady or in transient. Okay, what else? Yeah, we have everything here, plus and then we're going to import, first we're going to activate, and this is from the beginning, activate the boundary conditions, the solver, and boundary conditions. Okay, and this is from the beginning because we do this maybe in here. Okay, so we check if we are transient and steady, and then we are going to assign the boundary conditions. Like those are recharge, EVT, evapotranspiration, and drains. Those are the main ones because we are going to simulate a pristine, not a pristine, but a not required basin. That means that it's a basin that do not have reservoirs, that do not have channel diversion, that do not have land cover shapes changes, and so on. Okay, so assign the boundary conditions, and then we run the model, and then we check the we're going to check the water balance, the global water balance. Let's put global water balance, and then we are going to import results, and then we are going to do water table on cross section. Wow. Cool. So this will be a quite good tutorial. Okay, so let's start. First, we open the ModelMuse. So we look for our ModelMuse. If you don't have ModelMuse installed, there is follow us by Hatariwater. We have a whole tutorial of how to install ModelMuse. Yep. And with all the package. And then we select a new MODFLOW model. New MODFLOW model. Next. Yep. And then we say that we are going to use the no grid distribution, but here we can use 4 aquifers. We say that the first one is alluvial, and this is upper fractured aquifer. We don't put such long name. Middle fractured aquifer, and this is lower fractured aquifer, and this is, let's say that this is -40. Don't worry. Okay, and then we say no grid. Okay, this is the MODFLOW model, and nothing appears because we have selected no grid. Oh, sorry. Cool. Now, okay, in the description of this video you are going to see some files, and you're going to see some files, you're going to see the input data, that is the data that we are going to use for the model, and the model data, that is actually the files of this model. So you will have the whole data where to make the model by yourself, or like to open the model and work with it. Okay, so in the input data there are some shapefiles, and there are some a one raster file, plus there is some this is to set the water balance, because, or like the recharge and evapotranspiration, because actually they do change along the model. Okay, so first we go from file, import shapefile. So as we say, on the files that you are going to get the description of the model, there is the input file, there is the shapefile. In the shapefile we go with Cancha basin extension. Okay, and we import it, and then we say set values of enclosed cells. Yes, and then it goes to two formulas, because we are going to make it active from data sets required, later definition from model top to lower fractured aquifer bottom. Okay, nothing else, and nothing happens. Okay, why nothing happens? Because actually this if you see this coordinate, I mean this x-axis and y-axis are not on the extension of our shapefile, and ModelMuse do not have like an option that say zoom to this layer, but we can sort that out pretty quick. let's say, let's go to objects here, object, and let's say unused object, because actually the shapefile that we ported is unused. We open it, and then we go to okay, here, used to set grid cell size. We say, okay, we wanted this to be our cell size, and then we say 200 meters, because our cell size will be 200 meters wide, and then we put okay, and nothing happens. But now our object is to use to grid cell size. It's used to define the grid cell size. Okay, and then we generate the grid. We generate automatically the grid angel. This time, because this is quite basic tutorial, we are going to say that we don't want, I mean, because the model can automatically rotate the grid in order to fit it better with the results. But no, in our case it won't be this. Okay, and this is where it appears. Now it's the x-axis and the y-axis are on the range of our coordinates. Okay, so this is our basin extension, and the this is the grid that we have generated. Okay, here let's go. I'm going to go back here. So we say define it by shapefile, and then we are going to say define active zone and inactive zone. Why? Because like this is the basin, and on the basin you have a no flow boundary condition by default. So here in all this is a boundary condition. That is actually that these cells are, you don't need it to be computed on your model. So you have to set it as inactive. In order to do that, there is a way around. So let's go to data, let's go to datasets, let's go to required, hydrology, active, and we say that our model is false, so it's inactive. Yep. Okay. And all our model is inactive. How do we say that our model is inactive? Because if we say show active, nothing happens, because all our model is inactive. But we say we go to with the red arrow, and then we select this. We go to object properties of this file, and then we say position lock, because actually we don't want our basin to move, because we know that our basin is there, not anywhere else. Okay, and then we go to datasets. In datasets and hydrology, we say active, and we say active true. Okay, and now only the cells that are inside our polygon are true. Okay, and all the cells that are outside are inactive. Okay, cool. Now we define the solver. This solver for this type, because this is on the andean this is an andean basin, and it has a huge difference on altitude. So what we are going to do is, in order to solve this higher complexity, we are going to use MODFLOW and MODELMUSE and say, and it has a very smart recommendation, say maybe it will be useful to change to activate the upstream weighting flow, and you can do it here. We are going to do it. Okay, so we have activated the MODFLOW and MODELMUSE, then we go to MODFLOW package and programs, Yep. And here in flow we change it from LPF to upstream weighting package. Okay. Then we select the boundary conditions. Boundary conditions. We are going to say that is recharge, that is evapotranspiration, and there is drain package. Those are the three main packages that we're going to use. In recharge, we have to say that the recharge location is in top active cells, because in Andean basins, since there is a lot of difference in altitude, some top cells are inactivated because actually the water table is below, but it doesn't mean that the recharge cannot seep to the lower parts. Okay, cool. Now we have activated them. So if we go with our plan, we have activated the solver and boundary conditions. Then we are going to import our raster then. Our raster then, we are going to import it as, it's not a surface grid file, it's a gridded data. No, ASCII raster file, it's an ASCII raster file. So sometimes I in raster ASCII file we go to the files and there is a RST file and this is the raster file. Okay, we can assign it already from the beginning to model top. That could be a good idea for you. Sometimes, I mean, if you want to change the surface or line, you want to see some specific, like most advanced tasks, you set it as a different you state it as a different data set and then you apply to model top, but don't worry about that. Okay, and then we are going to do that is the average point in cell. That, what does it mean? That we are using a raster DEM that has a resolution of 30 meters by 30 meters, but our cell size is 200 meters. What if you have 7 cells or maybe 6 cells, and then you have all those 6 cells wide and 6 cells, so we have 36 cells, around 36 cells, and it will select, if we say average point of cell, it will create an average of the whole of the values of these cells and it will put the average as the elevation. But sometimes we use this point closest to cell center, so it will calculate which is the from the raster, which is the cell that is close to the cell center, and it will apply this. It's up to you what you will do, but I will suggest that you do a filter method. Otherwise, if you do a filter method, like the project is related, like you decrease the weight, because otherwise you will deal with the whole extension of the raster file. I mean, and then you don't need it, because I mean, if you remember, you have 36 points that will just summarize it in just one. Okay, wait a minute. Okay, cool. So we say model top and then say set value by interpolation. Yeah, there is a sorry, there are some consideration in this. I'm not going through that. Maybe I will do another tutorial. I will leave you my Gmail, if you are looking this and then you find it interesting and then maybe you wanted some specific case or something might not be clear, just write me, okay, and then maybe I can put another tutorial or something like that. This is saulmontoya@hatari.com, and then I can develop something like more specific on MODFLOW. Okay, so point close to cell center, we put OK. If we say set value by interpolation, nothing will happen. Yep, because we have to go to another place. It's doing progress here, but in the end, nothing will happen. Okay, nothing will happen because you have said it by interpolation, but actually you didn't define the interpolation method that will go to model top. If you wanted to set the this, you go to whether you wanted to see the surface. We will go to datasets. In datasets, we go to layer top and model top. The interpolation method is known. That's why nothing happened. But we are going to say that is I suggest fitted surface. Okay, we go to apply, and then it's where it's evaluating, and now it happened. Now it has, like if you see in the cross section, it has already the elevation. Okay, but our lower bottom is in fact at the 0 meters, and our basin is about 3,000 meters. So we don't have a groundwater flow model of 3,000 meters thick. So what we're going to do, we go to layer definition, lower fracture bottom. We're going to say that our alluvial bottom, we are dealing with andean basins, and andean basins, the alluvials are not huge due to the erosion and so on, and we are going to say that the alluvial bottom in formula is model top minus 15. It's a simplification, but so far it works well. Okay, and then we go to the lower aquifer bottom, and they say that is in fact, let's say that is 3,000 meters. I can move it. Okay, cool. And then I'm going to put some. First, we put apply. Otherwise, no one of our changes will have. So we check model top minus 15 and 3,000, and then we are going to say the aquifer. The middle aquifer is, I'm going to put, is model top minus aquifer times 0.5 plus lower aquifer. And then if you have said that, type this correctly, it will appear here. Okay. And this one is 85. What I have done, okay, close. What I have done is this. So if I go to a cross section with this here, and then I put this. Whew. It will take some vertical. There is so much vertical exaggeration for me. Maybe 5 is okay. Yeah. Okay. Cool. What I have done is this formula actually says, okay, this edge will be at the difference at the half of the thickness plus this one, so it will be at the middle of this difference, and this one will be 85. So what is mean in the beginning is that this is 50% of the total thickness, this is 35% of the total thickness, and this is 50% of the total thickness. Okay, just this is what you will need to remember, because what you will know is that hydraulic conductivity depends on the depth. So if you set a whole hydraulic conductivity with depth, I mean, we have a model that has 600-meter depth, like you will be setting some errors in defining the deep groundwater flow. Okay, so that's why I suggested just to put more hydraulic conductivity here, less here, and even less here. Okay, check, 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 check. Cool, so we have imported them, and then we are going to assign the one alluvial plus 3 fractural rocks. Okay, we are going to model layer groups. In layer groups, all by default, all our aquifers are confined, but we know that our alluvial won't be confined, and as well uh, and just the lower, we know that the lower aquifer will be always confined, but maybe the middle and the upper could be whether or unconfined or confined. So we say this one we put it convertible, we say this one in convertible, and this one in convertible. Actually, this model runs with just 4 layers, but it could be necessary that in further models or like more deeper models you will set more layers. Like actually on consulting work we deal with 13 layers, 18 layers, 24 layers. Okay, now according to our plan we have set assigned the 4 layer um, confined convertible. Okay, no, sorry. Okay, yeah, well, we did this. Well, we are going to say the hydraulic parameters. This is very important. We go to data, we go to data sets, we go to required, we go to hydrology, and active. Those are required because actually you need those. Active. Yeah, we have already done that because we have said the active part and the inactive part. On horizontal isotropy is 1 because we for us the hydraulic conductivity in one axis is different from is the same in the other axis. Yeah, by default MODFLOW has hydraulic vertical anisotropy. What does it mean? That is that K, or the hydraulic conductivity on the horizontal plane, is 10 times higher than in the vertical plane. Okay, in this time we are taking out this anisotropy because we are going to put different K's as with depth. So the K will be actually defined as lower, like if you go deeper. Okay, the initial head, this is very important. The initial head, this is the initial head that the algorithm needs to define to enter the this is what it needs to do the iteration of the matrix. So we say model top. Okay, and K, yeah, okay, here we put a edit formula. We're going to put a logical condition that is called case in the index. We are going to put layer, that is on greater mesh layer, and they say case layer is like a consecutive if. Okay, cool. And case layer means if we are on the first layer is at the alluvial, and the alluvial has a higher K. Let's say that we're doing with alluvial and colluvial, that is 1 into the minus 5. Then we're dealing with 1 into the minus, this is the first fractured rock, minus 7. Then let's say that we are dealing with 1 e to the minus 8. Why not? and say 1 e to the minus. Okay, minus 9. So this is it. What it will do, it will assign different values according to the different layers. So we put OK, we put apply. Okay, let's check. We active, horizontal is 1. This one, this says that k on the x-axis is the same as on the y-axis is the same as on the x-axis, and on the z on the vertical is the same as the horizontal. It's okay. MODFLOW initial head is model top, and this one I don't use it. Okay, so we put apply, and then we put okay, and then we are going to check if what we have done is alright. So we go to data visualization, and data visualization, the color grid we are going to set to kx, apply, and then we are going to say log transform, because like it's changing 4 orders of magnitude, or maybe yes, 4 orders of magnitude. So don't expect a linear to represent linear transform to represent that. So okay, so if we go here, if you see lower of the screen, I mean here, it will say 1 10 to the minus 10, 10 to the minus 8, 10 to the minus 7, and the smaller alluvial is 1 10 to the minus 5. Cool, cool. Okay, let's go to our plan. Yeah, okay, we're going to check the MODFLOW time and check if we're in steady and transient. MODFLOW time, and we are going to check if these are steady state. Cool, this is steady state, and if it will be transient, it will be this one, but in this case steady state is running on seconds, and it's running just 1 second. Well, this is the default for steady state. Cool. Oh, this is new. Cool. This is a converter of time units. That is new on this. Okay. Cool. Yeah, we have checked the MODFLOW time, and then we are going to sign. In this case, I will apply a uniform recharge and uniform evapotranspiration to this model, because we know that in fact it changed, and I will explain how those changes. But in order to do the linear regression could be a little bit trickier, and I want to make sure that you finish this tutorial, and then that you can redo this tutorial on your own. So I'm not going to use the distribution. First, I'm going to import to assign the drain package. So say file, import shapefile, and on the shapes there is a rios, that is rivers. Okay, and this we say that it's intersected cells that are, and this is very important, that is a single multipart object, because if you say that it's a separate object, each reach of the river will be an object, and you will end up with a lot of objects, really a lot of objects, and you don't want this. Okay, cool. Okay, number of formulas 1, because actually the rivers are on model top. And then we go to features, and then we say drain starting time is conductance interpretation direct, drain elevation is model top again, and conductance is 0.01. The discussion about which is the model of conductance is long, Maybe we can talk about this and say which is the sensibility. Yes, let's say this value and it work. And sometimes it doesn't work, just write to me and I will give you an explanation how to deal with this. Okay, there is no parameter type, and then it goes from -1, I don't know why, to 0, because -1 to 0 is the steady state. Okay, and we put OK. So review, set value of intersected cell, single multipart object, because we want just the whole chain in network just to be 1, and then it goes on model top. On features, we define that it goes to from -1 to 0, that is on model top, and the conductance is 0.1. Okay, okay, I know this color visualization is really slow. It's making our representation very, very slow. So we go to data visualization, and on color grid we say no. Cool. Now we have our channel network, but I always do this. I go back to this one, um, just change the color because I don't like the our reverse spec. Okay, now we need to define the region, the recharge and the evapotranspiration. In order to do that, we import again file import shapefile, but we are going to import again the basin extension, and then say set value of enclosed cells. Okay, cool. And then formula of theta 0. Yes. Shape is just one, so you don't need to make it multi-part. We can apply evapotranspiration here, but just import it and then we change it. So we import it, okay, and it's here. You don't see it, but it's here. So we are going to put some object line, like say this blue, like light blue, and this is okay, and this is the polygon. Yeah, this is the object that will define our recharge and the evapotranspiration. Okay, let's talk about the recharge and the evapotranspiration. Here you will have the variety, the distribution of precipitation and evapotranspiration. So let's put okay here. Yeah, this applies for andean basins. I know that there are many places in the world, and then you will have another distribution. So be open about that. We have on andean basins this. We have the precipitation is higher with elevation. Yep. We have that the evapotranspiration is lower with elevation because the higher the elevation, the lower the temperature, and the plants will require less water. So we have this. So the water surplus, or like the referential water surplus, is higher with elevation because on the top of the mountains we will have more precipitation and the water will consume less water. So it will have more surplus that will be recharged and runoff. And on the lower part, you will have higher precipitation, lower precipitation, and more, and the plants will take higher, more water, so you will have less surplus. Okay, so and then there is a regression here. Maybe I can do another tutorial just to do regressions on recharge and evapotranspiration. But what we could do is just our basin goes from 3000 to 5000, so we are going to say that this is the main value of our basin. Why not? Okay, so we say like we are going to apply this value of recharge and this value of evapotranspiration. Okay, so we go once again here to our, and this is, let's call it condición de recarga. Okay, cool. And then we go to evapotranspiration, we go to -1 to 0. The evapotranspiration rate is, remember, is 1000. I just can pick this, is this one, but this is in millimeters per year. So if we have to divide it by this, so to change it to meters per year, to meters per day, and to meters per second, because we are dealing with meters per second. So this is the value of evapotranspiration. The evapotranspiration surface is model top, cool, and the evapotranspiration depth, let's say that is 0.5. That is actually related to the um, root depth. Yep, we can talk more about that. There is a huge discussion about it. Okay, so let's say that this is our evapotranspiration rate. Because we are dealing with meters, we are using the standard, the international standard of units, so meters and seconds. And then on recharge, we go again -1, 1, but our recharge is 150. No, this is the, sorry, this is the water surplus. So, and like, this is a quick water balance that I do. So our water surplus is just 155, but if you are in, this is mostly 50% runoff and 50% infiltration. So we have to divide this by 2. And we can do it in ModelMuse. We go to formula, so we put this, and then this is the total surplus. So if we divide it by 2, this is the recharge. And then if we go to, then we divide it by 1000, then we divide it by 365, and then we divide it by, okay, and this is our recharge. Cool. Okay, according to the plan, yep, we have the recharge and evapotranspiration. At this moment we need to save. So we go to File, Save As, and then you save it on model data, and you say modelo 1. Okay, and then run the model. Okay, when it runs the model, there is a couple of tricks that you will need to know. Save. Okay, there is the num file is actually what it, oh, I have some errors. The model can run, look, the model cannot run with errors. So let's say the errors give you some, the draining elevation is below the bottom of a cell at the following locations. Hmm. Mm-hmm. 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 Wow. let's see. I mean, let's with this one we select this. We want hide because we want to select the. Oops, sorry. Control C. Hide selected objects. Okay. I selected the rivers, and they say my rivers are on model top, and the elevation. Okay. I don't know what happened here. I don't know. Maybe I did something wrong. If I have done something wrong, just say model top. Here is model top, and here is 0.01. I don't know what have happened. Maybe it's an issue. Don't know really. Model top. Maybe it's because I have imported. I save my project, and then I run my project, and let's see if this error appears again. By there is this black window that is actually what it runs the model. Don't close it because otherwise your model will you will stop them. So here I don't have the error anymore. I just have warnings. Your model can run with warnings. Sorry, the English is not with warnings, but it cannot run with errors. So with warning is okay because there are many things on the model that could be a warning, and we can talk a lot about that as well. Okay. Cool. What did it say? My model is saying that I have some convergence issues. Okay, and let's say what else? There is a lot of discrepancies, and those discrepancies could be from a lot of issues. And what it really makes you a numerical model is that to deal with these discrepancies and errors. And let's say what is the discrepancy? One of these main discrepancies is the drain package, and this is the conductance. For some reason, the model have on the iterations, like the drains by the conductance that we have given is taking so much water out of the system, but this water is actually not coming from the system. So that's why there's a discrepancy between the drains in and drains out. Usually there are two ways to deal with this. The first way is to increase the number of iterations, but the second way is just to decrease the conductance. So we go to the rivers, and we just said that is one, that is one order of magnitude lower. We save, and then we run. This is the compilation. Then what you see here is how the spatial data is transforming into MODFLOW files. Maybe I can do in the future some tutorials on FlowPy. That is actually a Python library that runs on QGIS that do MODFLOW. It really depends. Really, you like it, if you send me comments and so on, we can go more and deal more with this. Okay, now I think that we got it. I think that we are close to it. Why not? Cool. Now it has decreased because it was 100 the last time, and now it's lower. What can we do? We will do two things. We will increment the iteration by 50, and we are going to decrease the conductance to the half. And this will, I think, that will be okay. So we model packaging programs. So on flow, no, yeah, on solvers, on MWT is running with 100 iteration, let's say that it will run with 150 iterations, the maximum number of outer iterations. And once again, we go back to the rivers, and then we put this conductance value. I recommend you to learn the paper of the drain package, that is actually the manual, and save, because you can run the model without saving your changes, and this can be very this can lead you to a lot of errors. Could lead you. Okay. Waiting. Okay, remember, please follow us at facebook.com Hatariwater, twitter.com Hatariwater. Follow us to this YouTube channel because we will be posting many tutorials, and we want to do very hard stuff on ModelMuse and on other softwares as well. The actual running time is higher because actually is 150 iterations. Cool. Again, we cannot pass this. Let's see what has happened. It is. Neither. Look, I do believe that I have few water, or like my hydraulic conductance are so small for this. I will do just one more time because it's actually that was not the purpose of this tutorial. But let's say I will go to hydrology, and then we are going to say that the upper aquifer is 1 to 5 times, no, let's say 110 to the minus, or 7 to the minus 7, 1 to the minus 7, 1 to the minus 8, because actually the water cannot infiltrate, is my feeling of. Well, let's see if this works, otherwise I will have to go deep and to see what has happened. And there is no problem because even with these discrepancies we can import the results and see and make our cross section. That will be a reference to know what is going wrong. Remember that all of these files will be on the description of this video, so you can download it and use it on your. is even worse. Wow. Okay, data. Really don't know what happened. Yes, I will return to the values I had it, and then I wanted to show you the results from there, because and then I will go back to application programs. On the solver I will go back to 100 iteration because I want the results quicker. Save it and run it. Wow, something is going wrong, don't know why exactly. Well, let's say there is two. No, the drains. Why the drains is always taking so much? Once, one more. Let's go to this one. Model top. I decrease it one order magnitude lower. I think that I need. Yeah, this is will be the last one. Sorry. Okay, now the discrepancy is very small. Let's see what this discrepancy is. Yeah, it's really small. Well, and okay, we. Wow, why there is so much? Okay, we are going to see the results. We import the results. The results is with this one is the HDS. We are going to see as a control grid. Or maybe let's see as a color grid. Is with this one. Then we can see this. I think that I have some solution around that, but this goes on the discretization of the lower part. And then the last part of the tutorial is to do a cross section. So in order to do a cross section, we go here and we go none, we go head, and we do cross section, data set, optional model results, 3D data. No, water table, and water table we put this one, and then we change color. And then we take out the color grid. And then if we do okay, and this is the across section, and maybe if you want it fancier, like you can put it here, and this is like any illustration that you have on your hydrogeological books. Okay, really thank you, and really thank you for your patience. I know that groundwater modeling is a really hard stuff, and because you have to deal with the iteration, with the matrix and many other factors, that's why maybe this one, for if you do surface hydrology, this one is really much complex. And I hope that you follow this and you hope you like it, and I hope that I can see you on following tutorials. Thank you.